Hello and welcome. In this lab, we will be performing a triaxial test on fine-grained cohesive soil. The test you will be watching is a CUPP, which is a consolidated, undrained, with pore pressure test. It will cover standards ASTM D2850, ASTM D4767, and ASTM WK 3821. We will need the following items to perform this test: our soil, a triaxial setup, and a compression frame. I need to explain the material for this test. Typically, this test is ran on a cohesive fine-grained soil, i.e. silts and clays. These samples are usually ran on undisturbed samples using a drill rig and a Shelby tube sampler to obtain. The sample is extruded from the tube. After we log the sample in, we will cut out the portion we are going to use for our test. This sample should meet three criteria: fine-grained, homogeneous, and 100% saturated. For ease of testing and time constraints, I will be using a clean sand for this demonstration. Now a little bit about the setup. We want to have our sample at 100% saturation, so it needs to be placed into the test setup as quickly as possible. Once we have our sample, we will wrap it with filter paper to act as a wick so we can move the water from the top to the bottom of our sample easily. This will aid in the saturation of our sample. Even though the sample should already be at 100% saturation, during the setup procedure, we will get air trapped into our setup. We will need to be able to remove that air, and the filter paper will aid in this. Then we will place the filter paper on the top and the bottom of our sample and set it on the base of our chamber onto the porous stone. A rubber membrane will be placed around the sample so that we can control the internal pore water pressure and the external confining pressure. Then we will place the top of the apparatus, which also has a porous stone, on top of the sample and seal the top and the bottom of the membrane using O-rings. Once this is done, we will place the outer chamber over the sample and bolt it down to create a watertight seal. Then fill the outside chamber with de-aired water using this burette, which we will use to apply our confining pressure. Once the chamber is filled, we will apply a 10 psi confining pressure. Note, we always want to make sure that our confining pressure is larger than our pore water pressure. Now it's time to get as much air out of the sample and sample setup as possible. This will be done by pushing water through these two burettes. One is attached to the top of the sample and the other to the bottom. By putting 5 psi of pressure on the bottom line and forcing the water in and pushing the air out the top. Once we do not see any more bubbles coming out, we will reverse the process and push the water in from the top and wait for all of the air bubbles to stop in the other direction. We will repeat this process while moving and agitating the sample until no more air comes out. At this point, we need to find out how saturated our sample is. We will do this by using Skimpton's equation, which is called a B value. This basically states that if you change the confining pressure X amount and the pore water pressure changes the same amount, you're 100% saturated. If it changes less than that, then that is your saturation. For example, if your confining pressure changes 10 psi and your pore water pressure changes 8 psi, then you are 80% saturated. We need to be 95% saturated for this test. So let's show you how we will accomplish this. Making sure our pore water valves are closed and looking at what our current reading is, we will then change the confining pressure from 10 psi to 20 psi, a change of 10 psi, and observe where the pore water pressure changes to. We need to get our sample up to 95% saturation. This will be done by increasing pressure to compress the air bubbles trapped in the sample and replace the voids that are created with de-aired water. Also, by increasing pressure, we will be able to force some of the air into saturation into our de-aired water. The one thing we need to avoid is over-consolidating our sample. Our sample will have come from a certain depth from our site. The pressure that the sample feels from the overburdened material or the material above it gives us our effective pressure. We do not want to exceed that during our saturation process. To avoid that, first we need to make sure we know what that pressure is. By checking for our B value or our saturation, the sample does not take on that pressure. It is taken on by the pore water. This is how we can increase pressure in our test and not change the effective pressure that the sample feels. So let's change the confining pressure to 20 psi and the pore water pressure to 15 psi and open our drain lines. As you can see from the movement of our water in our barrettes, we have consolidated the air bubbles in our sample, created voids, and you see the water flowing in to fill those voids. We will watch the water level in the barrette until it stops decreasing, and then take a new B value and see where the saturation stands on our sample. We will repeat this process until we hit 95% saturation. Once we have completed the saturation process, we will move on to the consolidating of our sample. This is done very simply. Let's say that we have an effective pressure of our sample of 30 psi. And the pressures we used to saturate our sample were at 30 psi confining and 25 psi pore water pressure. We would adjust those pressures to have a difference of 30 psi. So they would be 55 psi confining and 25 psi pore water pressure. We would open the valves and allow the sample to drain, which will allow the sample also to consolidate. Looking at the barrettes, you can see that the water is being squeezed out as it is consolidating. We will watch the barrettes over time until we were able to get two readings a half hour apart that don't change. At this point, we will consider this sample to be 100% saturated and consolidated. We are ready to move on to the final phase. Time to shear our sample. We have two conditions available in which we can shear our sample, either drained or undrained. In the drain condition, we are unable to measure pore pressure, so we would have to run our test very slowly. Depending on how cohesive the soil is, depends on how slow we have to run it. It can take hours or even days to make sure that the pore water does not take on any of the load. We will be running our test in an undrained condition. Because we can monitor the pore water change, we can back the load out that the pore water takes from our equation, which allows us to load our sample rapidly. So to make it a drained or undrained test is very easy. Either these valves are open for a drain test or closed for an undrained test. So we will close the valves and seat the piston to apply our shear force. Rapid means we can shear it at 0.02 inches per minute per inch of the length of our sample. If we have a 5-inch sample, our shear rate will be 0.1 inches per minute, which will allow us to shear our sample between 5 and 15 minutes. Let's look at the pore pressure and shear curves as they develop. As you can see in the pore pressure curve, that as we start the shearing process, that the pore water is taking on additional load. When our sample starts to shear, our soil picks up more of the load and the pore pressure starts to decrease. If we look at the load versus displacement curve, we see that the sample is still increasing in load and has not hit its maximum shear load yet. This is important to note because our sample is in the process of shearing but has not physically sheared yet. We can stop this test and use it to get our other two data points. The sample that you are going to use for your data were 3 different samples that were set up in 3 chambers, consolidated separately and sheared separately. The data points you will use were strained to 20%. Another way to get these results is by using one sample. A lot of time you will be unable to get 18 inches of the same material out of a Shelby tube to run 3 separate samples. So if you take one sample, get it saturated and consolidated to your first point, you can shear it to the point that on your PQ curve you have come off of the S-shaped part of the curve and onto the linear portion of that curve. Then you can take that value and use it for that data set. Let's say at 5% shear. We can then back off sigma 1 and apply our next consolidation pressure and shear it back to 5% and repeat that process for our third point. This is called a multi-shear test. This should give you the information you need to know where the data you are going to analyze came from. That concludes this lab. For additional information, please refer to the student lab manual and get help from your TAs and instructor.